statistics. So we understand the concept of statistics, and then I'll quickly review Dulles plot, because that's how we can see Bose symmetry, and then I will talk of CP violation in D meson using Dulles plots and Bose symmetry. Okay, so it's like at first we say, what has it got to do with Bose symmetry? And here it was a very simple test. Then we are like testing Bose symmetry itself, but actually, to be honest, Bose symmetry is going to be exact. If things fail, so while I am saying there is Bose symmetry, it is not actually testing Bose symmetry, it's testing particle physics, because Bose symmetry will remain. So something would be wrong in my view if this is the case. Then we will test CPT violations in strong and electromagnetic interactions, so again using Bose symmetry ideas. And then finally we will have, not finally, that estimating SU3 symmetry violations. Again, the idea of Bose symmetry is used in Dulles plot to do it. And then finally, something that actually even surprised me was that measuring CP violation in baryons. Baryons are actually fermions. So, I mean, using Bose symmetry to measure CP violation in fermions, but yes, without it, there is only one method to measure the phase, and that's the method we proposed, this PRL. No other method has appeared so far, okay, and that uses Bose symmetry. Without it, the method would fail. And finally, I would say how Bose symmetry can be used to extract additional information that's hidden, okay, not done. And then quickly is summarized with very small thing. So, 100 years ago in July, Werner Heisenberg wrote a letter to Pauli, who was his friend and critic, the strongest critic, on the paper which is, he says, all my pitiful efforts are directed at completely killing off the concepts of orbits, which after all cannot be observed, and replacing it with this. So this paper, which is the interpretation or redefinition paper, where he redefines how to look at the atom and the thing. And so that paper is supposed to be the birth certificate of modern quantum theory. And there is this site at CERN, the link is works if you can go to the talk and see. So at CERN, if you open CERN page and say 100 years of quantum mechanics, it will give you these sites. A lot of interesting things. Original letters of Heisenberg. This is the letter, and then Pauli, Heisenberg, and Fermi. And so what happened was, very soon after that, people came up. So Heisenberg didn't quite, he was not competent with matrices, but people immediately, went through and did the thing, and he became very, very famous as a new quantum mechanic. Okay, so the story of Satyendra Bose. Actually, this is I think thing from book by Abraham Paes, where he says that the paper by Bose was the fourth and last revolutionary paper of old quantum theory. The others being Planck himself, then Einstein, and then Bohr. Okay, and his paper was the next important thing. So, and this is largely, a lot of interesting thing about Bose is available from this site, but a lot of other work is available in various encyclopedia and things, and lot of literature in American Physical Society journals also, that I'll show some of it. While working on the theory of radiation at catastrophe, Bose found that contemporary theory, which is actually Maxwell-Boltzmann, although he later admitted at some stage that he was not fully competent with Maxwell-Boltzmann either, but he realized that it could not predict results in accordance with expected results. And so he proposed first to propose that Maxwell-Boltzmann does not accurately describe the behavior of macroscopic objects. Bose argued that since photons are indistinguishable, okay, from each other, they cannot be treated we cannot treat any two photons having equal energy as being distinct, okay, identical photons. So they are producing an accurate result. So he ended up producing an accurate result using this non-distributibility. Now that was a major change, because all of classical mechanics had Maxwell-Boltzmann distribution, but particles were distinguishable, even with the same energy, distinguishing them. So Bose wrote up a small paper and submitted to the British Journal Philosophical Magazine, which rejected it. Okay, so this is an interesting thing. They rejected. It's not known why it was rejected, but they rejected it. Then he wrote on June 4th, 24. He wrote a paper. He sent a paper to Albert Einstein with a note. You will see that I have tried to deduce the coefficient 8 pi nu square by c cube in Planck's law, independent of classical electrodynamics, only assuming that ultimate elementary regions, the ultimate elementary regions of phase space have the content h cube. And I do not have knowledge of sufficient German, so he pleaded for him to get it published. And the interesting history is that on 2nd July 24, Einstein wrote back to Bose saying, "Dear colleague, I have translated your work. It signifies an important step forward, and I liked it very much. You are the first to derive the factor quantum theoretically, even though because of the polarization factor 2, not wholly rigorously." Okay, it is a beautiful step forward. So Planck had introduced the idea of quanta of energy. So you'd say, what was the big deal? He already had the idea, but it was the quanta of energy for material in the oven. So it was not radiation itself, but the radiation from matter. So it was different from what, and this idea had not, and that is the reason why people found it so difficult to derive the formula. Planck's derivation, as you can remember, is slightly ad hoc, but these derivation that I am going to show is something you would have done in BSc most likely. Okay, just that the importance may not have been emphasized, and the origin from Bose would not have been emphasized. So in in 1923-24, Compton effect had clearly shown that radiation itself consists of quanta, but still the derivation of Planck's law using that, and whether Bose was aware of all these things is not very clear. Some interesting work on Bose is his book by Wali. I can't find my copy. I bought it here outside the thing. So this is one of the things here. Partho Ghosh, counting in dark interferences, and there is an archive paper he has recently updated on this. And so this is a very comprehensive thing. And I don't know whether I should, since there are no students from MSc or BSc, maybe I should skip the derivation. And so you see, Bose, if you do it correctly, you find as 4 pi nu squared by c cube d nu, and this was wrong by a factor of 2. Bose had appropriate to multiply with this by 2 in order to take account of the fact of polarization. Okay, now he had realized this thing. Einstein didn't quite, in translation there is probably some issue there. I haven't gone through the detail, but this is sort of interesting. The first factor in emerges with a totally new meaning in Bose derivation. So the idea was that the number is fixed, the permutation of indistinguishable photons within a cell cannot produce new cells. Okay, and so I will skip this because this is a textbook derivation for the second part of Boltzmann thing. I was thinking the MSc students, how many MSc students are there? None. So I will skip it. Only one. Okay, then you would have done it already in BSc, or this would be better known to you. Interestingly, what I found that Raman and Bhagwantan were the first ever to measure, to experimentally determine this photon spin, explaining the factor of 2 as arising from the spin of the quantum, left-handed or right-handed. Okay, And so it was here that that experiment was done. So the spin of the photon was done only in 1931, I think. This experiment was 1931. I forgot to put the date. Corresponding to so the left hand right corresponding to the alternate signs of angular momentum. And Bose's critical insight was to consider the indistinguishable nature of photons, particle light, and to use the new statistics approach that did not distinguish between identical particles. Okay. So this was very dramatic and radical for that time, because nobody knew that anything apart from Maxwell-Boltzmann distribution. Yeah. Yes, that's right. They measured, it showed the boson spin, and the photon spin was one. The first one to do that. And the electron spin was measured earlier. I am going to point that out also. Okay, so photon spin. So the idea was, we had seen the photon, we knew everything was in place, but still to show that it is a vector thing took time as long as that. In 1931, I forgot to put the date.
Bhagavantam, I see. I see.
And
this is before or after Raman scattering? Before.
Just after that.
Wow.
So,
just to advertise,
please.
I have an article with me on boson blue.
Oh, okay.
Research will get it. Many of these things are there.
Great. Good. I should get.
Just for.
Yeah, I would love to. Yeah, because I am interested in this even for historical purposes now. Result of Bose, now called Bose-Einstein statistics, laid the foundation of quantum statistics, and especially the revolution of new philosophical concept of indistinguishable particles. Okay, so Bose actually, the truth, he written 2 papers and sent both of them to Einstein. Einstein translated them both. He commented about the first one. Second one he published, but then had a little comment below that saying that he didn't agree with something. Okay, and that paper is relatively unknown, but it shows the Bose's ambition in getting a full theory, and there was a small error, and it's beautifully discussed in this American Journal of Physics article that E.C. George Suzerson asked them to publish to settle that, it was a very important work. It was just, if only one equation had been correct, then it would have caused. So this is beautiful discussion here, but I don't have time to get into it. So Einstein, of course, adopted this idea and extended it to atoms and led to the production of Bose-Einstein condensate, which was experimentally verified. And so we have seen the idea of Bose-Einstein symmetry, and the other problem that was remaining was the Fermi's, but the other statistics. So integral spin. So we here, late 24, Pauli made a big leap by suggesting the idea of adding a 4th quantum number to the 3 that were then used to describe the electron quantum state. Pauli called his new quantum number as 2-valuedness, not described classically. Okay, in 25 he announced the exclusion principle. In fact, just a few months after that, he announced the Pauli exclusion principle, stating that no 2 electrons in the atom can occupy a state with the same value for the 4th quantum number. Okay, so this is just before Bohr doing away with the orbits. Okay, so he was Pauli had proposed this thing, and every electron had its own unique state. Other possibilities are excluded. That was the idea here. And later in 25, Samuel Goldspin and Uhlenbach, inspired by Pauli, interpreted the 4th quantum number, the electron spin. and there is this beautiful thing on APS that discusses this in detail, and it is interesting to note that Stern and Gluck experiment was done in 1922, and to their surprise, they had verified sort of that those days this is called space quantization, the Bohr-Sommerfeld thing. So they were thinking it's all wrong, and they said let's do the experiment to prove that this is wrong, and then found that this is correct. But nobody paid attention that in the Bohr-Sommerfeld theory you had 1, 0, -1. I mean, so with the half quantum number there. So that understanding was also not there. So you think a triplet. They observed a doublet. Nobody bothered, and it turns out that only 2 lines instead of 3 were because of possible spin. So the idea of spin was already there, and the factor of 2 cancelled out factor fixing everything. So, okay, so they already Stern and Gluck, if they had not relied too much on their theories, they would have said here is a spin. Okay, but because they were trying to verify a theory, and to their surprise they had ended up verifying something, they didn't expect to see this splitting, and they saw it. So there's a beautiful talk by Sandeep Pakwasa here. If it's not on our archives, I can give a copy. I have it, which goes through this story of how experimentalists always get the rough end of the stick, and so quantum mechanically particles obey different sort of statistics, which takes into account the discrete quantized nature of physical properties on a very small scale. There are 2 different quantum statistics: Fermi-Dirac, which applies to I always do this, which applies to half integer spin, half 3/2 piva. It is only for these fermions that exclusion principle applies. Bosons are particle with integral spin 0, 1, 2, 3 have their own quantum statistics. Both statistics applies. Okay, so now that we know that there is, I am going to use these ideas of Bose symmetry to extract something one would not have expected from. Bose symmetry refers to multi-particle system whose wave function remains unchanged when identical particles are exchanged. Correct? So that's what we want, and in order to utilize Bose symmetry, of course, if you have one particle decaying to 2, then you can hardly tell whether it's symmetric because it's just partial. If you have 3, then the exchange symmetry can be studied, correct, related to the third. So you look at the third particle, and so we look at how do you study 3-body. So how do you study such things? 3-body decays are Dulles plots, well-known approach to study 3-body decays, and a typical Dulles plot is this. This was done by Matt Barrett after our paper was read. So Asia Pacific Newsletter wanted to put news, so he drew this diagram for one of the modes, and you see there are complicated things that detail all kinds of structures that are taking place, everything that's happening. So yes.
So the pi are the ones that you would exchange.
Yes, I'll get to it. I'll get to it because this is the interesting thing. So this is like drawn for the k pi, and this is I think 75th birthday for Dulles in 2006, and his students put together. There was a meeting in France. So I had visited him in 2003 or 4, 2004 maybe 2003. He was such a nice man. He couldn't walk, but he had visited India just before that. I wrote to him and he invited, and he had his office first floor, so he had great difficulty walking. Climbed up, he sent me all details, a very nice, interesting thing. And there I told him that I want to do, symmetries based on Dulles plot. He told me, you're very ambitious, don't look at all that. So do what you're doing. Yeah. Yes, his student, and he has visited Math Science several times. There's a photograph of him outside. Rajesh did his PhD with him. and I think even Devakaran, was it Devakaran also, and
Once I was visiting Oxford,
yes,
I went to Dalit's office and introduced myself because very fondly inquiring about Rajaji
yes, yes,
many,
yes.
many years ago.
He had such a nice program. I mean, he was not well, but he still took me around anyway. So this is, so how do you do kinematics of a three-body decay? So in principle, you have 3 particles, 4 momentums, so you have 12 parameters that need to describe it. But then there are a number of constraints. 4 of them are energy momentum, 4 momentum conservation, right? So 4 constraints are there. The on-shell nature of the particles, 3, you are decaying them on-shell. Rotational symmetry of the plane of decay, and orientation of the rotational symmetry, up, this way, that way. So you have altogether 12 minus 4 plus 3 plus 1 plus 2, you finally have only 2 parameters that need to describe the kinematics of the 3-body decay. And so this is what, so interestingly Dalitz had done everything, and this Dalitz plot was actually very important for understanding K decays, okay, K 3-body decays, and that's how we built this whole thing up to do it. Yeah. No, this axis could point up or it could point down. That's right. That's what it is. And so the 2 independent invariants are mass squares, completely describe the phase space, and typically you have 3 invariants, which are the Mij squared, where Mij squared is the moment of Pi plus Pj whole squared, 4 momentum whole squared, and they satisfy a constraint, which is this. And so you have basically 3 of these, 1 constraint, so you have only 2 invariant mass squares that are independent. And you typically, in the notation of Mandelstam, you have the STU, which are defined like P2 plus P3, P1 plus P3, P1 plus P2, and absolute limits are on STU as m squared. And under exchanges, your particle 1 to 2, particle T, they go S to T and T to U. Okay. So these symmetries are there. Yeah.
Just have one comment.
Yes.
When you situate this in the context of relativistic physics,
Yes.
what you are doing,
Yes.
it's also important to remind ourselves that Bose symmetry
Yes.
is fundamentally conceptually entangled with Poincare symmetry.
Yes. Yes.
And the point that I'm building
Yes.
towards, and maybe you are also going to mention, is that an n-particle Bose state
Yes.
has to remain symmetric under exchange in any Lorentz frame.
In any Lorentz frame.
So
Absolutely correct.
a violation
Yes.
is in some sense both a test of either a violation of Bose symmetry or a violation of Poincare symmetry.
Yes, yes. What we are doing is a very simple application here, and so it's only a 2-particle state. So here what happens is that you look at the Dalitz plot, and this is typically the textbook plots where you can do it in coordinate x, y, and then the phase space for x is just this. So I'm not going to go through the detail because there are not that many students who haven't had a course. So, and most of us will find that interesting. And so you can do it in the polar coordinate or in the xy coordinate system, barycentric coordinate system, and you can describe them in terms of theta. Also you can have, angle, how you describe from which side theta is this, theta prime with this, which axis you take. So you have all these relations that are there, and they will be used because we'll play with the symmetry in the Dalitz plot. Okay. These sextants are related in the sense that you have these exchange of 1, 2, 3, 4, 5, 6. These sextants are just, for example, if I have like 4 and 1 and 6, it's like going T to U. T to U will take me 1 to 6, 2 to 5, 3 to 4, and so forth. And each one of them can be done this way. So distribution amplitudes inside Dalitz plot depend on the properties of the amplitude. variation in the distribution of events inside Dallas plot is a signature of matrix element or amplitude. Dallas plot would be symmetric under exchange of two particles, say 2 and 3, that is in a T and U, if particle 2 and 3 are identical under the symmetry and they exist in even partial waves. So if they are in odd partial waves, then even if they are symmetric, it won't. And so we will use these simple ideas, and we will show CP violation in D mesons and in Dallas plot. Now, it's a very simple idea that yeah.
So this, whether SPU is just
Just choice because I combine.
P1, P2, P3 can be relabeled.
Yeah. So all we do is once we define them, we can just say if I want to switch P1 to P2, it's like S to T. So that correspondence can switch.
So in your notation, the P2 and P3 will be the identical particles.
It depends. In this most of the notation I have taken P2 and P3.
Okay.
But in some cases where it's convenient, I'll do the SU3 where it will be more complicated than that. So I've given these general things, yeah. So if CP is violated in this thing, the idea is it would exhibit a signature on the any particle x going to d naught bar y Dallas plot, and I'll show you that that's what's going to happen. Okay, when the neutral mesons are of course constructed from a daughter particle of definite CP. Okay, now this is sort of interesting because it was hard to convince ourselves that something like this is actually happening. For conceptual clarity, we will focus on B to D naught bar K, but then later on see that it can be generalized completely. We are not going to use the point that there is a V and a K there, it is going to use only this. Assume that there is no direct CP violation in the DD bar system. Okay, so let's start with that assumption. There is no CP violation, and that the D mesons are reconstructed from daughter particles in a definite CP eigenstate. Let us say that is a CP plus eigenstate, that is D is reconstructed in K plus K minus or pi plus pi minus, some of the most common things, and this was like one of the most important modes right from when I was a postdoc. So we studied these modes and saw how they will get affected. So this is what we will do, the CP in this state. So for we will assume plus, but there are minus CP states also, which I will not discuss, just that they are there. Note that we have constructed D mesons on flavor insensitive, they are not flavor sensitive. So you can't tag from these modes whether it came from a D or a D bar. Okay. So if you do that, then what is interesting is that you have reconstructed D mesons on flavor insensitive modes D and they are indistinguishable. In the final state, therefore, D naught bar are entangled. You cannot distinguish. You can't tell me whether it is V or a D bar, and therefore they are in entangled state. So what has happened is the identical nature of the particles, as you will see, has produced an entanglement of the D mesons. They would tag flavor because it will tell you whether a D or a D bar. That it is between the modes, and the singly capable suppressed modes are like that. They cannot distinguish. So you look at them, and there are modes which are CP even and CP odd modes, and so you track them in that, and you can get. So a little bit of primer on this. This is all standard stuff, but D meson can be expressed in terms of mass eigenstates and CP eigenstates. So the mass eigenstates are D1 and D2, and the CP eigenstates are this and that. And so here these are P and Q, which are the Bixing parameters, and the mass eigenstate can be written in terms of CP eigenstates like this, because there is a P and a Q. So you just add and subtract and you get this simple thing. The reason why we are interested in the mass eigenstates is because time evolution is very easy. Okay, mass eigenstates just evolve in time. Flavor eigenstates, Bix, and that's much more complicated. And they are given like this in terms of the mu1, mu2, where they are parameters that define the mass and the width and the mass difference and the width difference between the d and d bar. Okay. And for neutral d mesons, they get described, of course, as I mentioned earlier. I have been cutting pasting slides from various talks, so some bit of it is overlap. So what happens is P and Q in general are complex and they lead to CP violation. If it's complex, becomes CP violation. And in general there can be a Z, which I will use later, but this can lead to CPT violation. And so if there is no CPT violation, Z is 0. Okay. And P squared plus Q squared is 1, giving this. And in the limit of exact CP asymmetry, P is equal to Q. Sorry, again I invented it. Sorry. P is equal to Q, and therefore D12 is actually mass eigenstates, CP eigenstates are equal, and they are just sums and differences. Both the D mesons are reconstructed in F plus state, and if no CP violation exists, that is that same mass or CP eigenstate D1, if no CP violation exists, you have constructed with the CP plus eigenstate, and therefore is the same as 2D1, correct? Because you have reconstructed in CP plus eigenstate. CP plus eigenstate is exactly the D1 plus eigenstate is D1, the mass eigenstate, correct? And so you have reconstructed in CP plus, that is D1 state, if there is no CP violation. And so what has happened is both the mesons are reconstructed in F plus, and so both of them are D1. And therefore, the Dulles plot, because they are two identical particles, must be identical. So, Bose symmetry demands that Dulles plot will be fully symmetric under exchange of D mesons. Okay. Any difference in the Dulles plot under the exchange of the two D mesons must be a signature of CP violation. Since Bose symmetry is more fundamental, one of the states must actually be a D2, right? One of the states must be a D2 that has, because of CP violation, decayed to F plus. D2 would not decay to F plus if there was no CP violation. So you have violated CP, that is why you have. So if you see any asymmetry, then that's a signature of CP violation. And that is how, see, Bose symmetry led to this entanglement of this state, and that allowed you to measure CP violation in this, just from looking at the Dulles plot. Okay. And so how do you look? I'll do just a little bit of algebra to show you that it's all so simple. Okay. So what you have is the B coming in, you'll work in what is called the, sorry, my big fat fingers, Gottfried Jackson frame, where you actually have the B and K direction to be the same, Z axis, and then D and D bar go back to back. And this is described in terms of the STU would be described in terms of this, where A and B are fixed with the masses, and theta is the angle between the K and the D. Okay. And as you can see, if I want to go from D to D bar, theta goes to pi minus theta. And so that symmetry on the Dulles plot can be seen. Okay. And if you look at it, how does it look? This is the T is equal to U line, and then T less than U and T greater than U region are here. And that's the sides that we will see. This is how it will be. And under theta going to pi minus theta, cos of minus theta. And that's what you have. And this is how it would look typically. Oh, just the amplitude, how it will be. Amplitude, when you work out the metric bond square, this is how it looks. The intensity of what angle these particles are going.
So if you take the bond square, then if there is no CP violation,
No, what will turn out that both sides will look equal. So the distribution of events would look equal. I'm just showing the theta distribution here, that how the events get distributed.
Yeah, if there is no CP violation, they should look equal when you
They
take
look equal. Actually, the sad thing is that it is only this when you look at the proper diagram, which has 0 to one normalized by D. It is just this blob where there is events appearing in this. Okay, and nevertheless that's good enough. So you put all the constraints, it is just this tiny region. All right. So how am I doing on time? Huh? Huh? 35 minutes. Okay. So good. Okay. So the state we wanted to look was K, D naught bar, right? And you want to do it in terms of mass eigenstates, because mass eigenstates evolve straight away there. So I rewrite these and do in terms of D eigenstates. So I rewrite using the equation that I had given earlier. So I had given D naught in terms of mass eigenstates with the P and the Q, and so I write that. Okay, and this is antisymmetric under P to P3 exchange, as you can see, and this is odd under T and U, and this is even under T and U, and this is symmetric under 2 and 3. Okay, I may have got a sign wrong, just that may be, anyway, yeah, I may have got a sign wrong, but anyway. Now there is CP violation, let us assume that there is CP violation and it decays to state this. So the plus eigen D plus will go to F plus as the amplitude this, because no CP violation in this, but it will decay with a epsilon I, which is CP violation in terms of AI. So if epsilon is non-zero, that means that there is CP violation, because I am allowing D minus to decay to F plus. Okay, and so the amplitude for this is given in terms of this, where epsilon is there, and so from that equation I have just written this, and I put it back into the whole thing and reconstruct where I am decaying for plus and plus, the D mesons are both decaying in the plus eigenstates. I get this, where AE and AO are the sums of ATU plus AUT, which is symmetric part, and the odd part is this by cos theta. Okay, because the ATU minus AUT, it will switch sine and theta, so we are normalizing by theta, and then we get the even and odd part. So the amplitude is actually even plus odd cos theta. Okay, so we have got this. Similarly, we could have done with a minus eigenstate also and got an equation like this. Epsilon is a measure of CP violation. Oh, because the first meson and second meson, just to be sure that D naught bar everything, so it's epsilon 1 and epsilon 2 is just put for that.
But it is equal now.
In principle, yes. No, sorry, I'm sorry, it's a mistake. It's for the mode I take. F plus need not be the same mode. It's mode 1 and mode 2. Sorry. It's like KK, one could be KK, the other could be pi. Correct? And that could be different epsilons for those. And that's what we'll measure.
You cannot look in the same mode, only
If you look at the same mode, it will cancel. I'll show you. This cancels. Because this one doesn't have any CP violation. This is too small, epsilon 1, epsilon 2. Okay? And here it cancels, so there's nothing. It's all real. And that's what we'll see. So what we'll measure is this famous asymmetry called a KK pi difference, which is at phi sigma, an established signal of CP violation in D. Okay, that is stood test of time, and our paper came out, I think, after the disputed asymmetry came up, and people debated whether it's going to stay or not. It fell down quite a bit, but now it's a phi sigma result. In the same mode, it will be identical, because both particles are decaying, so both D mesons are going to same particle. There is no difference between the two. You haven't created. So if you look at that's it here. If they're same mode, then there will be no asymmetry. Yeah. So you can create, and this is the minus. So I put a minus here. This is a plus mode, minus and plus. So you can do that, and you can work it out. And it's easy to extract all of these. Delta is a strong phase between AE and AO, and we have done that, and you can actually show that you are actually measuring if you choose one state as kk and the other as pi pi, then you are actually measuring the difference between the kk and pi pi. Okay? So that difference automatically comes at Dallas plot. If you have identical thing, then of course there is nothing to distinguish. Whether it's a D, see, even if it was a D or D naught, so even if there is CP violation, both of them will equally break symmetry and go to. So they look still distribution identical. And the difference in the distribution is now proportional to this, directly. Note that the parent particle B or the nature of the accompanying particle plays no role in the kind of direct CP violation under consideration. So it is only the momentum of the K meson that was important, because that's what played a role in the Dalitz, right? And the mass of the. So we could have considered anything. We would have considered a thing like E plus E minus going to Y, and you could add up, or even a multi-body final state where Y is anything. It could be pseudo-scalar vector, a multi-body state. All you want is that D naught and D naught bar should be there in that, and they should be reconstructed CP eigenstate, and you can combine everything. Generalizing, you can say that this is the final. And the interesting thing is that, as I will show later, that it doesn't matter in E plus E minus or anything, any collider, anywhere you produce D naughts in pair, reconstruct it, both symmetry will tell you that there is correlation if you look at them in CP eigenstate. Okay, so this is the paper was published saying that tests for both symmetry, but the truth is that it went through straight away, even before we realized that we shouldn't be saying tests of both symmetry. It is tests of particle physics because the nature of these two. So for example, we take this mode of, I've given a very small, you take these K mesons, even B would be okay, you decay to plus pi naught, and you have different particle decays into each one of them. Then you see that because I have two identical particles here, that 2 and 3, this side and that side will be symmetric, left-right symmetry in the plot. All I have done is I have distinguished them by constructing them in different modes. Okay, so this is very interesting. If you see any such thing in the Dallas plots, then it is clearly some breakdown of your particle physics. You are not seeing what you are supposed to be seeing there. There could be something else. Okay, very unlikely. But test, yeah. Yes.
Fermions,
Yes.
then the mod scattering will say that there will be a line of zeros in between.
Actually,
Bunching.
That's what Murthy and my student Dibrupa looked at. It's a little bit much more subtle than this, because neutrinos is one example where that happens. The other examples of say, identical particles is not possible, but you could do them under G parity. So it's under G parity you could make things and do generalizations, but I don't think, I was thinking later on we'll look at it.
Okay.
But that is not, neutrinos has been looked in detail, and it is a much more subtle problem because of the left-handed neutrino business. Okay. So now suppose we are all identical particles. You construct them in, two of them in identical mode and one of them in a different mode. You can always construct it. And then you see that only half the Dulles plot can be constructed, and they must be symmetric. And this is something which is very easy to do. Lot of events, already Dulles plot exists. Now only thing is, convince the experiments, at least put a limit. Okay? Put a limit, how much asymmetry is there. But manpower shortage. And this would be a nice thing, you're putting a limit on it. And that's when I am a member of Bell, though now only technically. Yeah, go ahead.
So, can you turn this around and, I know that you mentioned
Yeah.
limitations of manpower. Is it at least feasible that you can imagine putting limits on the
QCD theta because of CPU, because you're looking
Yes,
for...
yes, yes. So there are, yes. In fact, a lot of things you can.
You said it.
Correct,
Okay.
correct.
Okay.
Yeah.
I'm sorry, I
so
didn't see.
CPT theta, and this is what we have.
No, I meant QCD theta, the
QCD
strong
theta.
interaction.
QCD theta, yes, if there's CP violation coming from that. For example, that's one of the things that, if something is broken, that you would find that yes, there is something wrong in your conventional thing, which is sort of beyond the conventional thinking. That's why these are important tests.
Yeah.
And while they are mentioned in particle data book in the older experiments, we have done it. New, we have so much data, and techniques are so much more simpler, but we are still not doing it.
Yeah. So I mean, normally the way these things work is that the data will say that if theta is non-zero, it is smaller than this number,
Yes, yes.
and then
Yeah.
smaller than this number. You
But
just keep on making.
Yes, you keep on making it, and it needs to be done because eventually.
Absolutely.
Maybe somewhere.
And at some point it becomes
Like-
uninterestingly small.
Correct.
Yes.
CP violation in D mesons was one such thing.
Yes.
And we said no CP violation ever. Okay. If it is seen, it is really new physics. Now it is seen, and we debate whether it is new physics or not new physics. So this is how it goes. Yeah. So this is another interesting thing that came to our attention, was that if there is CPT violation, what happens? It's a much more complicated system, because now you have first you want a system where there is no weak interaction, because asymmetry will turn out because of CP violation also. So no weak interaction. So you look at electromagnetic or strong interactions, and there are many modes where three body decays happen through strong interaction or electromagnetic interaction. And the amplitudes can always be written in general in terms of this sine theta, where the theta is the angle in the Dulles plot, okay, that I had mentioned, from the y-axis clockwise, counterclockwise, and so sine theta and cos theta, where these coefficients are in general complex, okay, and under CPT theta goes to minus theta, and you have S and R going to S and R conjugate, and CNR going to CNR conjugate. When CPT is exact, then you have the AR theta as AR theta with theta going to minus. So you find that both CPT are exact, then you have, if you have to make this condition with CP, so of course CP is assumed in all these cases. If CPT is exact, you can say that this condition leads to S and R being 0, because otherwise this would switch sign, and this being purely a boundary. Hence Dulles plot is symmetric under theta going to minus theta. So if CPT is exact, you would find this. Okay, that's what should happen. Now, if CP is exact but not CPT, then there must be an observable effect under theta going to minus theta. So we can use that to extract CPT, and so here I'll just do a little bit of detail, add CPT into this by adding this epsilon s, which are CP violating parameters. These are strong phases between this, because after all, you are looking at strong interaction or electromagnetic interaction, there could still be phases, okay, and so you put them in and you look at this, and what you are going to do is you are also going to look at modes which are self-conjugate. That is, there is no distinction between mode and conjugate mode. Okay, the final states are same. If that is the same, since you have a CP conjugate amplitude, it is sum of both, and therefore it is this amplitude. Okay. So what we do is we construct the amplitude for this phase, but in Dulles plot you do mod squares, so we do a mod square here, and what turns out is that under theta going to minus theta, this is proportional to this term. This term survives only if CPT is violated and leads to a symmetry in Dulles plot. So we actually, the details in the paper show how you can measure these parameters. Okay, there is enough observables there to measure the parameters. So if CPT violation is there, any violation, which is very important to pin down, because let me say an important thing that I forgot to mention earlier is that CPT tests are done. People say, oh, my advisor had derived the test when he was a graduate student. Okay, mass of particle and antiparticle are same, tests of CPT, decay bits are same. But masses of heavy particles, and how fine can you measure them? So the tests will be very weak. Here in Dulles plot you have all these events, okay, so presumably your test will be much tighter. So this is a new way to test it, and it's much tighter. The problem is, if you look at one decay, you'll say I have only 10 to the power 7 events. That's like a good mode, right? And really strong signal. 10 to the power 7 signals, and then looking at errors and seeing distribution Dulles plot. How well can I do? Then this idea of Dulles prism. Since we showed that it really doesn't matter what mode you are doing, right? You can combine everything together and project down to the same, so that all you want to do is project all the Dulles plots so that this base is the same. Put them all together, and so we coined the word Dulles prism. And so it doesn't matter what mode, which channel, whatever, anything. It can all be combined. And so you can test CP, CPT, other erroneous things in particle physics which we call Bose symmetry. All of them can be put together and combined. And the reason why we are able to do is because we are only looking at projections at the base. That's all. So you can actually combine a lot of data in the Dulles concept. Yeah. Just to enhance the number of events, because you can look at in all the modes together, and the question is statistics should not limit. So the question, the whole purpose is you should be able to get a very good bound, and I think it's worth pursuing them, because tests of CPT etc. just by measuring masses and bits, you will never be able to make sure that there is nothing happening. For all. Actually, for CP, CPT, Bose, everything you can do it, and that is the idea. So the Dulles prism, and the interesting thing is that if you are looking at E plus E minus or anything as the initial state, then it doesn't even matter if there initial state radiation or anything else happening, or final state radiation or anything, because it's all independent. So it's just the particles that are being in correlative pair that we are interested in looking at. So that's what happens. Okay, I have some of these ideas mentioned again. You could look at anything, J by psi. Okay, so the idea, my student was very good in drawing these caricatures and cartoons. So, but very interestingly, he presented the idea, and I have borrowed all these from him. This was in his thesis. Yeah, all these papers were. I think, yeah, it was in his thesis. Yeah, it was in his thesis. Yeah. I mean, sure. I mean, it's representation of something you have done. No, that's the only thing banned. Okay. All right. So, how much time do I have? Because I have. 20 minutes, great. So I'll be in time then. Good. So, we all know that SU3, which is a Plaber symmetry, is broken because U, D are close by in mass, but S is very heavy. And how do you calculate how much is broken? How much is breaking? Well, there are estimates, people say 20%, 30%. What is the experimental evidence that this is so much? And then it should depend on what region of parameter space you are looking at. If you are looking closer to resonances, maybe yes, it's bigger because there. So it is a question to which only experimental answer can be given. But how do you experimentally test CP violation, SU3 violation? So as you know, SU3 consists of isospin with a T spin, U spin, B spin, and since you can't calculate, there are just empirical estimates. Mass differences between certainly will lead to SU3 breaking. Not possible to estimate binding energies from QCD calculations since resonances lie. So even if you do lattice and give some sort of breaking, it's not true in resonance regions. Okay, resonance regions could be quite different. So you really need to get an understanding on the Dulles plot how much it is. And so it turns out that you can again use Dulles plots idea, and I'll start with this mode, but it can be generalized to various modes. So up quark has different electric charge than down and strange and cannot be treated. So this is the idea that is important to look at. And there's another important concept that I'll just bring to attention. That is, the pi 0 is of course a pure isospin triplet state. But if I look at pi 0 in terms of U spin and V spin, it is not a pure triplet state. It is a triplet and an octet mixed here. Okay, and so this is very important and complicates things. So if you look at K pi 0 pi plus state in isospin, it is this. In U spin, it is quite different looking thing. Okay, and see, the coefficients have changed, things have changed, because I have had to worry about which one I am taking. Okay, and that is very important. So now this is the interesting part, how one can apply. So let's say physicist A, he decides to choose isospin. He says, I trust isospin, I like it, I am going to work only in isospin. Okay, so he says, in your mode K, pi plus pi 0, pi plus and pi 0, if I plot the Dulles plot, pi plus and pi 0 exchange means T and U exchange in the Dulles plot. Okay, but physicist B says, no, I want to test U spin, and I am not going to worry about this isospin. You will never find a violation there. So I am going to look at K pi exchange, which is the ST exchange. Okay, if both isospin and U spin are exact, are individually good symmetries, Dulles plot must obey the symmetries concluded by the physicists. Correct? Both the physicists should find, if they exactly both of them will find the same answer. But this is impossible unless the amplitudes are either symmetric in both S and T and T and U, or antisymmetric in both S and T and T and U. I will show this in the next sheet here. If the amplitude, this is fully symmetric, that is under S to T and T to U, so this is fully symmetric. No, nothing. I mean, all we are doing is the Dulles plot, we are taking K pi pi states. So two of them are sort of isospin identical because I am using isospin. The other K pi will automatically be U spin symmetric, and if I want to do V spin, I have to generalize to the concept of G parity for V spin. Okay? Yeah.
Q3 is exact.
Yes.
K and pi are also identical.
K and pi are also exact.
Okay.
Correct. And maybe I'll just complete this and I'll go back and I'll point out something which I had not done. So you can see that if I were to actually look at symmetric state going under S to T, it will be fully back. So it's fully symmetric state. It will remain if I have this exchange. If I have under the two exchanges, if I have symmetry, it's a fully symmetric state. Okay, so it's SS. If I have antisymmetric, it is fully antisymmetric, because whatever I do, if I S and T, it switches sign. If I do T and U, it switches sign. If I do S and T, it again switches sign. So it's antisymmetric. So it's fully antisymmetric state. Okay. Now, if I do symmetric under the first and antisymmetric under the other, symmetric under the first S and T, it's same. But if I do this to this, it is, and therefore you see, if you go through this chain, you will see that this is 0. There is no symmetric antisymmetric state that can exist if both U and I are good symmetries. That is the important thing. So you see, already I can see that only simple state survives, and same happens with antisymmetric symmetric state. This will also go to 0 with the same argument. I just flip and that happens. Pardon? No, what is happening is that, see here it's all boson states, k pi pi. I could do k k k. So here I have given examples of different modes. Actually, these are just some of the examples that we have studied in our paper. Okay. Pardon? AA is allowed because it's not 0. AA it's fully antisymmetric because if I flip the 2, every time I flip it switches sign.
No, but if I switch two bosons, then it's getting a minus sign, no?
No, yeah, but that's an antisymmetric state.
But it should not be allowed for two bosons.
No. I'll explain. So this is under S and T. If isospin rule is violated, then I would find that yes, under exchange. Yes, if it is exact, correct. So the question is that how do I write a general wave function if it's all correct? If it's antisymmetric, you will still find that it is valid. No, if SU3 is exact, you would find this as the bit. You can make. So the question is that there are partial waves, there are other things. So you have this amplitude surviving. Yeah. So the point is that if they are good symmetries, then under these exchange, amplitude can be written in this fashion. Correct? Because after all, so this is what, so the general amplitude must be symmetric, and antisymmetric. That's all. There is no symmetric, antisymmetric, symmetric. So if you are going to write this amplitude and say this is the case that they are all correct, then this is the only option. So by making both of them antisymmetric, I in fact induce the fact that they are, so it is like not just one of them. If you do one of them and keep the other symmetric, it doesn't exist. So the k pi flip and the pi pi flip, that is still the same, because so let me go here, and of course so I have this amplitude and I can immediately do the mod squares, and the symmetric amplitude, because Dulles plot is amplitude mod square, so the symmetric part is this plus that and the antisymmetric is this, and so you can see different functions will be constructed. So the events in the first part of a second, third will be equal, and they are equal to this. If U spin, V spin are all exact, now V spin is not implemented in this mode trivially. You have to add D parity to do it, okay, because you do a conjugate mode and carefully do it. Then you will find that all sections are exactly equal if all of them are obeyed. So it doesn't matter if k, pi, all of them are identical boson, then yes, you will find complete symmetry, and that shows up here. Okay. And if isospin symmetry there is, then 1, 2, 3 get mapped to sextants 4, 5, 6 respectively, and note that, so actually it's 6, 5, 4, and if isospin not broken, then this relations must hold, and that gets translated to these kind of asymmetries for isospin, U spin, V spin, various things can be done. But I am not going to bore you with it. But the interesting thing is the fact that I can choose one symmetry, you can choose another, and the results must match if they are both exact. Okay. That forces and leads to conditions, and those conditions will be violated if either asymmetry is violated. Now how to determine which asymmetry is being violated? Because under, as I showed here, under isospin and U spin, different segments will match. Okay, mapping between different sextants will be there, and this is cast in this. So detail is given in our paper. Okay, now I'll come to the last paper.
Presumably U and V are
Much worse, yes. So you would expect them to be broken, but once you measure them on the Dulles plot, you know where it is being violated, whether it's a resonance region, where are they very good. It's possible that in certain kinematic regions they are very good, and especially when you are applying theory or constructing models to do that, then you ought to know where So what we do is we do a calculation and say broadly 30% sp3 breaking is taken into account. That may be putting the baby with the bathwater. You know, you might, go ahead. Yeah, that's a bit that I'm saying. I'm a member of BEL, but they have to do these things.
Oh, it's not yet been
Not yet done. The tests are all, you know, it is just, so that is part of the reason why I insisted on taking the high position, because I felt that, okay, I'll force experimenters, but it's very difficult to force experiment. You know, they're short of manpower, extremely short. And so it's always like this or that. Anyway, so this is the thing that we were really excited, and it is one of those, I think, yeah, go ahead.
Do you know this very old paper by Dashen, who talks about the patterns of spontaneous symmetry breaking
Yes.
in the context of flavor symmetry, SU3?
Yeah.
And his argument is from the early
Correct.
70s.
Early 70s.
I'm sorry, I'm not remembering
No, but
the
I have
details of
yes.
this. And his point is that roughly speaking, the direction in which you approach the symmetry breaking point
Correct.
is a very sensitive question.
Sensitive question, correct.
And
So that
I'm
is
sorry, I do not remember any. I will go back and look at the paper and tell you.
He look at it dynamically. What we are
Yes.
doing is the kinematic effects of that.
Yeah, I think that
That's why.
the 2 points are not unrelated.
Yeah, it is. See, SU3 is already broken. We know that, and how it is broken,
The
we don't know that.
direction of
Because of
breaking,
masses.
yes.
We don't know whether it's broken because of resonance effects, other things. So that's all. But so we're looking only at kinematics. Okay, let me get to CP violation, which is the my really interesting thing. See, one of the outstanding problems in physics is to explain the baryon-anti-baryon asymmetry of nature, which is the required CP violation. For Sakharov condition to hold and or a standard model, it's possible that Sakharov condition holds simply because there is no CP violation in baryons, but you have leptogenetics other options. But nevertheless, since you have seen CP violation in mesons, CP violation of that level must also exist in baryons, correct? And CP violation was actually first proposed in baryons was first proposed in 1957 by my guru, and it was only seen this year. The conclusive evidence, which is like 3.7 evidence actually, is only now. And so this was a point when I wrote this paper, it was like not yet seen. So it's very important. But not only must you see CP violation in baryons, but you want to measure the phase in baryon decays to compare it with the CP phase in mesons and to test standard model. Because if larger CP violation is seen, then you may actually have a different mechanism also occurring in baryons or somewhere else, or for some reason you don't see it in, so we have to understand the reason, and therefore any discrepancy between the measured phase of baryons and measured phase in mesons would be straight away new physics. Okay. Also it should shed light into the idea of what leads to baryogenesis problems, and the original CP violation in that. Clean measurements of weak phase has been possible in B mesons, of course. D meson weak phase has not been measured. K, you have these parameters, but is not at all clean. So there is no reason that clean measurements will necessarily be possible in baryons. That was the thing we thought of, and so we wanted to explore it in detail. Obviously, since we know the CKM structure of standard model, we know that is the largest in BTU transition, and so we expect that the anti-triplet 3-bar B baryon is the best place. They were the lightest and they have the largest phase in the decay. So that will be the best place to look at CP violation. And yeah. Oh, 3-bar, it's in the quad structure there will be a triplet light state, then there is octet, duplet, everything is there. There is a section of heavy baryons. So they are like They are, no, just like baryons have the octet and the decuplet. There is a triplet of the B baryons, and then there is a sextuplet. So there are of SU3. This is actually, actually what happens is that, the triplet of SU3, if you look at it exactly, if you do full SU5, then this is it. So in SU4 there was this, and so that's how it works. But this is in SU3. So it's a 3-bar mode that you want to look at. Okay. Mendel CP violating phase is not simple. There are of course many hurdles, otherwise people would have done it. In order to measure any CP violating phase, must satisfy certain conditions. One is that the well-known that CP violation is observed must have both the weak decays. It must be 2 interfering amplitudes with both weak decay, weak phase and strong phase. Okay, and so you must have an interference using 2 different amplitudes. In B it is very easily done because you have B directly going to F and B0 going to B0 bar through mixing, and that decays to the same final state. So you have 2 amplitudes and you find this thing in B meson. In baryons, the baryon number forbids any oscillation, any such thing. So this is B and B bar. So you can see CP violation for sure, but measuring it, you need to create an interference. Okay, and that interference is not easy to create in baryons. And further, there is another interesting feature, that at least one of the decay amplitudes be reparameterization invariant, because after all, to define the phase, you can't just add 2 complex numbers with each amplitude unknown. So let's assume which clean measurements. What I'm saying is clean measurements, which means I don't want somebody to tell me that this amplitude is so much from theory, because I don't trust. I'm a theoretician, but I don't trust theories when it comes to fundamental physics. Okay, I will not take it. So I want it clean where I can measure every element experimentally. Okay, and that's what I'm looking for, ideas like that. So that was the key point, and so we came up with this thing that no clean measurement is possible in many modes, and we realized that that's because of reparameterization invariance, such that what I'll explain this if possible. So in the meson case, you measure the amplitude 1, the amplitude of the conjugate mode, and the argument, the angle between, because you have B0 to B0 bar interfering. Okay, so you have these amplitudes, but you still don't know which is the A, what is the B. If these are the amplitudes that are describing it, then you don't know what A, it could be any one of them. It could be this or that, and unless you know one of the amplitudes fully, or there is no phase phi in one of the amplitudes, you can't do anything. So that was the key thing we realized, and that made it very difficult to baryons. You don't even have the interference between the Z and Z bar, so you don't even know the angle between this. So you certainly cannot do these measurements in any arbitrary mode that you choose. So you must be very careful in the choice of mode, because if you can find a mode where you find one CP eigenstate, then you can manage. Okay, so this was the problem in choosing what you could do in alpha and beta modes also, say as modes that measured in mesons, the alpha and the beta. And so we came up with this mode. Actually, we studied the entire table of all the 3-bar decays and could find only one mode where you could measure this. Okay, and this is the cascade B minus. It decays to a sigma prime 0, sigma prime because it's a spin 3/2, so it's written by prime. Okay, so it's a spin 3/2 system, and this is a pi minus, and it can also go to sigma prime minus pi 0. Okay, and then what happens is sigma prime decays to a lambda pi, and so the neutral mode decays to this, the charged mode decays to that. this mode was chosen except nothing else worked due to reparameterization invariance. And of course, you know how this works. And we have this mode with a pi minus pi 0. And once I have a mode with pi minus pi 0, the bosons are symmetric because after all, once it's produced, it's only strong interaction that's going to play. It's already weak decay is done. So strong interaction is the only thing that's going to happen. Then they're identical. If they're identical, then I can use Bose symmetry. Okay, as long as isospin holds. And that's why it's very important to figure out how good this is. 2 minutes, I'm almost done. So this diagram, if you look at it, if you look at this diagram, the sigma 0 mode, the one with the sigma 0 prime, has both C and P. But if I look at the minus, it is only coming from the P. And so I have one mode which has a well-defined phase. So I can clear myself off from the reparameterization invariance problem. Sorry. And you see, the point is that here is a typical plot, a standard average. Without enough knowledge, you would just do this. You would see this, and look, there is no interference between this and that. So why bother with further decays? You bother with further decays because this picture is not a complete picture. You must have implicit interference between these two modes due to Bose symmetry. The implicit interference is appearing because both modes are producing the same final state, right? Without being able to tell which came from where. Okay? And if you look at this, then the pi minus pi 0 is either in state 1 minus 1 or 2 minus 1, and they are identical. So if in odd isospin, that is 1 minus 1, it must be antisymmetric under exchange, spatial exchange, and this must be even under exchange. So this is how we end up, and since the sigma y isospin half violating symmetric decay, so you would find that delta I 3 half contribution cannot arise from parametric. Oops, sorry, what did I do? Next sheet. So what I am able to do is I am able to separate the penguin contribution by looking at the isospin symmetries at the Dallas plot. And when we do that, actually you find amazingly, if you take carefully the full 3-body mode and then do the proper calculation, you find that the interference patterns are clear, difference between mode and conjugate mode. Okay, you can see, and that's enough to give you measurement of CP, exact measurement of CP violation. You can get the phase. And so Bose correlation obviously plays a fundamental role in this new approach to measure CP violation. But I would never have thought that Bose, so every time I thought when I would look at baryon, I was thinking, let me think of Fermi. But it turned out that Bose, first of all, it was difficult to find modes, but that's how it turned out. And my last slide is that, you can, in fact, surprisingly, this vector k pi mode was known for a long time. Okay, they have been measured. Very first few modes to be measured are these k pi modes, and people have done this isospin decomposition in terms of the amplitude. Sorry, big fat fingers. And what happens is people said, okay, this is a quadrangle, but I don't know the angle between these two, and since I don't know the angle between these two, this is like of no use, because it's like, I can be at any angle, I can't tell any phase. I can never do a phase measurement using this. The problem is that if I had fixed a diagonal, I would be able to do everything, right? So the question is, how do you get this diagonal? So this is an information which this mode simply doesn't give. But if you have a decay, which is typically k star goes to k naught pi naught, and a k star plus goes to k naught pi plus, of course goes to other modes also, but you take this, and then what happens is, I have a pi minus pi 0, okay, sorry, I'll take only these two modes. These two modes, you see, A3 half, same sign, this switch sign. That switch of sign in the half modes is interesting, and both of them will give the same final state. So the Dallas distribution will be, the amplitude level will be under the exchange even under A3F. So the A3F amplitude is the even amplitude. So if I look at the amplitude and extract it from the Dirichlet plot, I have extracted my A3F. In that case, what happens is my quadrangle is fixed. I can do a lot of work and I can get extract a lot. Even this has not been done by Bell instantly. The student who did the thesis on this from TIFR, but this is more complicated. He left it halfway through. He did the Dirichlet plot, but didn't want to go further. But that's how it is. But you know, you measure these things. So both symmetry, in conclusion, I'll say, first of all, let me put this, thank you, finish on time. This. So the conclusion, I think I have already been emphasizing a lot, so no need to bother. The only thing is that, you know, it's amazing how this simple symmetry can play so much role in, I never believed. When I did Bose symmetry, I said, okay, this is done. It's a symmetry and condensed matter people will use it. I never realized that this is how it will turn out here. Thank you. Thank you. Thank you. So, yeah. Go ahead.
Sorry, I followed the details not very well, especially for the baryon CP violation. But just to ask you, so in the recent measurement at LHCb of lambda sub b decays, you have an interference between a tree level term and a one loop. And there's a strong phase, which is a bit of an issue there, because you are trying to ultimately extract the weak phase. Here, the interference is between two different
What is happening is they are only seeing a signal. We are trying to measure the phase. So you can see the signal, but they can't measure the phase ever. Because they don't have, you know, all the information and the interference between mode and conjugate mode. If you don't do that, you can't extract that additional phase. So they can see a signal. CP violation signal is seen. But extracting that weak phase requires this interference, otherwise you don't get. It's like, you know, a two-slit experiment, so you can say that yes, but I need that phase. If I don't do, so that is where their limitation is.
I see. But here, are you plagued by uncertainties due to a phase which arises from the strong interactions?
Or there is enough information to solve out everything, simply from experimental data. So all the thing I have done here, everything is extractable purely from experimental data from the Dirichlet plot alone.
I see.
Everything.
I see.
That is the interesting thing in these things. There is nothing left to theoretic calculation or uncertainty of any kind. That has been the. So all the work, I have done little, but done only where I can, I don't have to, so somehow my contempt for, you know, calculations which are non-perturbative and done in an ad hoc fashion is, but perturbative things absolutely important.
And sorry, just to follow up, and you know, given our present estimates of the weak phase and so on, if you estimate the asymmetry in this decay, is it something Bell can definitally get a good bound on alpha?
Unfortunately, baryon, they can only measure, they can only measure in the charmed baryons. So charmed baryon is very small, but I am completing that also. But LHCb can.
LHCb can do this?
Can do it, yes. And this is what they should expect. They are saying it's difficult, but they agree that this is, I mean, certainly very interesting and this is difficult. And while they don't cite it in their paper, our paper was before their thing. They don't cite our paper, but in the talks and things they do say that, you know, eventually the phase has to be measured. They may be thinking that there are other ways. We have gone through it exhaustively and we know there's no other way. We haven't come up with anything.
Especially if you don't have the strong phase uncertainties, if it's so clean.
That's right, very clean.
Then it's
very clean.
Really very interesting.
Correct. So everything, actually there's a very elaborate thing and I haven't put them here, but a very elaborate thing how it shows that every single thing can be extracted. And and with enough thing from the Dirichlet plot that certain sign ambiguities when you solve can be resolved because there is redundancy in all the angular distribution. So that is the interesting thing. So this was a PRL, one of the, we have 3 PRLs that went through almost smooth. No, 2 without it. This was one of them. And that is all because it was clean signal. And that's it.
Thank you.
And this was also, go ahead.
Yeah, let us have this final question.
Is it
it okay? or-
Yeah, we can, so,
Okay. No, a couple of small questions, maybe the
Yeah.
second one we'll discuss offline. The question relates, you said that this was the lowest mass thing where you could probe this strong CP violation. Now, what about the delta resonance, the delta plus and delta minus, which could perhaps be produced in something like heavy ion collisions? or
You
PP
mean for the
collisions or
baryon
something?
CP? No, not for the baryon CP. Which mode?
Baryon,
Baryon CP. Okay. The problem is that what happens is that you need to have the
So there's something that prevents you
Yes.
to see.
So
such
what
a
happens
thing.
is that if you were to violate the reparameterization invariance, so not all modes, we want one mode which gives you a pure phase. And so there are all the deltas, all have been studied. In this, all the modes, deltas, everything with the baryon decay we have done. It turns out that we haven't found anything else where I can do this reparameterization invariance.
Okay.
So then I have to rely on something saying that I can ignore this mode that's small. So that is the issue. So that is the second level, but we are doing it. So this is in the where I am doing a B to U transitions. There is B to U weak decays. So there are other modes. So actually the penguin, it's a B to D. There are also the B to S penguin, which you can come, and those modes that are there. Now, unfortunately, there the electroweak penguins are also there. Here there are no electroweak penguins because they are very small for this B to D. So that's why we are looking at this mode. The other mode is also done and written up, and the students submitted. The archive said that substantial overlap between this paper and that. He didn't change. So then either look, it's your paper, you are the first author, change it and get it done. He didn't do it, but it sits in the archive with that mode. But these are the only two modes. One is not so clean because electric. This is very clean.
okay, so rest of the questions and discussion probably we can take during the lunch, and it would be good if there are some more questions from the students. Probably you realize there are so many things to do. So let us thank Rahul for this.
Thank you, and I probably forgot to say that what a great feeling to be back home.
Yes. Yeah, you should come quite often.
Yes,
Yeah.
certainly will.
Okay, so let us thank all the speakers of the morning session, and when will we be back? Shivaji, is the